Today I'm going to talk about base factor functions. This is a joint work with Rachel and Dr. Valen Johnson. Before I go, before I start presenting, I would just like to give a very brief overview of what base factors are. So base factors are basically, so if you have two hypotheses of interest, say H0 represents the null hypothesis and H1 is the alternative hypothesis, and you put some kind of priors on the null hypothesis, say pH not at a prior, specify the prior on H1 as pH1. So the posterior odds, the, the ratio of P of H1 given the data and pH not given the data can be represented as the base factor, which is represented as the marginal of the data under the alternative hypothesis and the null hypothesis, multiplied by the prior odds. So if you have the base factor and you specify the priors on the hypothesis of interest properly, you have some kind of an estimate of the posterior odds. And you can draw your inference based on that. But this comes with certain challenges. So this marginal is calculated by putting some kind of a prior on the parameter of interest, say theta, and that prior, we specify that prior as pi theta, and this marginal is calculated by the likelihood multiplied by the prior, and then marginal with respect to the prior. So when we have one specific parameter of interest, but we have many nuisance parameter, then this integral becomes quite cumbersome, and also specifying so many priors induces some kind of subjectivity, drawing inference. In order to overcome those issues, Dr. Johnson proposed base factor based on test statistics. So how to overcome such difficulties will be discussed through the course of this presentation. Now, consider this contingency table. Suppose we want to test for the independence between site and blood groups. So under the alternative, we would have to specify priors on each of the cell probabilities and the marginal probabilities. In that case, we have, and the calculating the marginal becomes quite cumbersome. Under the null, we would have to specify priors on the marginal probabilities, and in that case also computing such a high dimensional integral becomes quite cumbersome, and hence the computation of the base factor. That will also induce certain subjectivity through the specification of so many priors. In order to circumvent that issue, Dr. Johnson proposed base factors based on test statistics. So if we consider this example, what a typical frequentist would do is to do a chi-squared test under the null hypothesis that the test statistic will just be a chi-squared test statistic with zero non-centrality parameter, and under the alternative that will have certain non-centrality parameter involved. So what we test, instead of testing for the independence, we would test if the test statistic, say H, our null hypothesis would be the test statistic H is a chi-square distribution with certain degrees of freedom, and our H1 will be if this H given the null centrality parameter is this. So we would just specify a prior null centrality parameter and calculate the marginal based on that. So a high dimensional integral. I don't understand the data. You get this, I just don't get what you're asking. So it's just a contingency table, and you're looking for association between side that's part of my body. What is that? Yes, some kind of like things. Data. I like that. Okay, so it's just an example that constructed. So those are blood groups, and these are some parts of the body. So you just want to you just want to maybe, so this is the classification of cancer patients, but that is not of importance. So just consider it to be a contingency table where you want to just identify the association between two variables.
I suggest when you put data up on this on the talk, you actually you understand the data. So that's got nothing to do with cancer. This, I mean, if you have a blood group, your blood group is going to be the same throughout your whole body.
Yes. So
I'm kind of confused about what that.
So I think this is.
So you're looking for association between two variables.
Yes, that's all.
Okay.
Yeah.
Get that bit, but it doesn't really match what your table is. So maybe kind of to explain your data a little bit better.
So I don't use this data in the talk. So this is just a simple example to motivate it, but it has nothing to do with the presentation forward.
I agree with you, but I dislike talks where they put a data set and have no idea of it.
Okay.
And no, you should not do that ever. Because right now you have like a completely meaningless data set and I don't understand it. And it's going to confuse everyone. It confuse me. Okay? Don't do that.
Yeah, so we will just place star on the non-centric parameter, compute the marginal under the alternative, and under the null, note that the distribution of the test statistic is completely known, so there is no need to specify any prior under the null, and that a high dimensional integral boils down to a unidimensional integral in that case, and that also helps us to avoid a high dimensional prior specification. But there is another issue with it, which is that it does not yet reflect the effect size. So that's the main drawback of the base factor based on test statistic. Dr. Johnson, Sandy, and Rachel, they dealt with this problem in a paper that was recently published in PNAS, where they expressed base factors based on test statistics as functions of the effect sizes. Now, so data from a normal. So mu is the effect size here. And if we had, say, some sigma square here, which was known, we standardize it. So just mu by sigma is the standardized effect size. So that's how we determine the effect.
So do you know normally, do you have a prior on your effect?
Yeah. So we will discuss how to reflect that belief. That will be the main motivation of the talk afterwards.
So from a basic standpoint, you sort of have an idea what your effect, the size of the actual effect, which wouldn't have the frequent test type.
Yes, exactly. Yeah. And also when we have replicated designs, we also have some sort of notion regarding the variability of the effect sizes. So we would also incorporate that in our project.
How would you know the size of the effect, for example, in conclusion system? If you looking from association.
So that will be reflected in the prior belief. So we will put a prior on this effect size.
So how can you find that? So if you think there is an association, we're kind of figuring out what joint probabilities are.
What do you?
Well, you have a continuous table of candidates between two variables.
Yes.
And you're putting a prior. You know, the joint is no longer productly margins, right?
Yes.
So now the effect is going to be sort of in some sense the difference potentially between the joint minus product marginals. Potentially. I don't know. And that's my problem. How do I know what my effect would be in something like that? A contingent table and testing for association between.
So that's why we would express the base factor as a function. So whatever your effect is, we will plot the effect size on the x-axis and our base factors over here. So say you know that this is here. This is your effect size, here the effect size, and it all goes up to whatever. So whenever you have some kind of a prior notion about it, and here we plot the base factors. So if you have some kind of a notion about it, you can just input that and you find the base factor.
And if you have no information about it,
So, so in that case, you can just use base factor based on test statistics that I discussed. So in case you have, so when you have replicated designs, we usually have some notion regarding the variability of the effect sizes as well. And that will be discussed through the course of this talk. In this context, I will also briefly mention how non-local alternative priors play a role in this. So what a non-local alternative prior is, these are the priors that assign negligible mass to the parameters that are consistent with the null hypothesis. So if 0 is your null hypothesis of interest, a non-local prior would typically look like this. Which would separate your null space from the alternative space. So it would assign 0 mass to your null space. A typical example of the non-local alternative prior is a normal moment prior, which you can see in this example. This density is proportional to the raw moment of a normal density. At the null, it puts 0 mass on the parameter space. And I want you to note that the modes of this density are specified using the 2 hyperparameters. We will need this through the course of this talk at the end. Now here, the continuous red and blue lines, they represent non-local normal moment prior. And as you can see, as R keeps on increasing, the density becomes more peaked and peaked. So that hyperparameter actually controls for the variability of the effect size. So if you know that your effect size lies somewhere around here, you can actually reflect that through your prior belief, through the choice of R. Is based on test statistics. Under the null hypothesis, as I mentioned, the test statistic usually follows a standard normal distribution. Under the alternative, it has a non-central or a normal distribution with some kind of a mean and variance. We just put a prior on that, and we get a base factor based on test statistics. Now, for each test statistics, I want you to remember for the time being that they are functions of tau squared. Same for the t-test. We put a normal moment prior on the non-centrality parameter. And here I also claim that this is a non-local prior because we restrict R to be greater than 1 so that the non-local alternative prior does not collapse to a local prior, and K is a positive integer. So that shape parameter of the density is always greater than 1.5, which is a rescaled chi-square more than 3 degrees of freedom. Negligible mass at 0 alternative prior, and we get this base factor, which is also a function of the tau square. And the reason I'm mentioning this actually is because later on we would see we express these tau square as a function of the effect size. And since these base factors are functions of tau square, they will become functions of the effect sizes. The same thing happens when we have a F test, and in the manuscript, we also have the expressions for the one. There is a huge gain when we use a non-local alternative. So when under the alternative hypothesis, our base factor converges exponentially, and under the null hypothesis, our base factor converges linearly, whereas if we were to use a local prior, the rate would only be linear. Now, as I had mentioned, till now, I haven't said how we are expressing base factor as functions of effect sizes, and that will be done through the choice of tau square. Now assume we just have a single study when we do not have any replicated studies. And for a single study, let us assume in order to estimate tau square that R, the other hyperparameter R is known. We express a function of the standardized effect size, in this case, which is mu by sigma. And we equate it with the prior mode. So if we were to consider a normal movement prior, our prior modes will lie at plus minus twice of R tau. So if we uh, denote this ratio as a standardized effect size, say omega, and express this, say, through 10 omega, and equate this with this, we just, assuming R to be known, we just get the value of tau squared as n omega squared by 2 twice of R. So tau squared could be expressed as a function of the effect size. And our base factors based on test statistics were expressed as functions of tau squared. And hence they could be easily expressed as functions of the effect sizes. Now, we still haven't considered the variability of the effect size. So when we have replicated studies, we reflect that variability into the hyperparameter R. So we assume a fairly non-informative prior on R, assuming R to be a greater than or equal to 1, say a truncated Cauchy density or a Jeffreys prior. And we consider the estimate of R to be the marginal maximum a posteriori estimate of R. So given these two hyperparameters, the test statistics for each of these replications, they are independent across all the studies, and their joint distributions are just a product of their marginal densities at each of the sites. And assuming a prior on R, this is the density proportional to the posterior density of R, and we are just considering the mode of the posterior mode of R.
Such close estimate because in most of the cases here, the map estimate of R was 1. So that's why these lines overlap. And these are the values for the other estimates of R. And as you can see, the base factor functions corresponding to the map estimate of R and R equals to 1, they gives the maximum evidence. Now it is natural to ask, since we are drawing our inference based on summary measures like test statistics, are we losing any kind of information or does it affect our inference? So in order to address that, we compare our method to a fully parametric method where they assume a bivariate normal model, where they assume the underlying data distribution to be distributed normally. For each of the replications, they put a stretched beta prior on the correlation coefficient. A stretched beta prior is basically a beta prior stretched to -1 and 1. And they assume a non-informative prior on the nuisance parameters. Now, how do we compare the two methods? So we find for each of the replications, we find the base factor using this method, and we maximize the base factor with respect to kappa. And using our method, we put R equals 1, and we maximize our base factor with respect to the effect size. This is a result of the comparison between the two. As you can see, the intercept is 0. On the x-axis, we plot the maximum logarithm of the base factor derived using our method. And on the vertical axis, we plot the maximum logarithm of the parametric base factor, that is the maximum base factor derived using the competing model. And as you can see, both the methods give comparable results, being the slope being nearly equal to 1. Now, in this prior, in the stretched beta prior, if we put kappa equals to 1, we get the uniform prior. And if we put kappa equals 2, we get this Jeffreys prior. So we do comparisons using those methods as well. In our case, in this comparison, particularly in this figure, we restrict the effect size to be greater than 0.1, since the prior puts 80% of its mass for effect sizes greater than 0.2, and we hope to achieve the maximum evidence in that case. So as you can see, this is for uniform effect sizes. For uniform prior, the evidence that we gather are almost comparable. And for Jeffrey's prior, we lose a little, since here the null is favored. The logarithm of the parametric BF gives more evidence in favor of the null in certain cases. But that does not affect our inference, because even our logarithm of the base factor also is negative, and it is minus 0.25 or something like that. So minus 2.5 or something like that. So it does not affect the inference in any case. Now, another drawback of using the fully parametric model is that the competing method assumed that the data is normally distributed. But when we plotted the scatter plot, we saw that in none of the sites, the data was normally distributed. So in many cases, like the inference depends on what the underlying assumption regarding the data is, and that can lead to deceptive inference. But in our case, we do not assume anything regarding the underlying data distribution. Now we will see another example where we have overwhelming evidence in favor of the alternative hypothesis. So this is a true test data where this is a very interesting data where they show you a color, say red, the word red is written in red, and the word red is written in blue. So what takes more time? And they test the difference between the two. So what a frequentist would typically do, he or she would do a frequentist t-test. And under the alternative hypothesis, we would have a non-centrality parameter. And here we would do a one-sided t-test, which is why we put a truncated normal moment prior on the non-centrality parameter. This is our effect size, the difference between the standardized difference between the two means. Using the same method discussed before, we choose tau square and express it as a function of the effect size. We consider the map estimate of R, and here we have 36 replications. So we typically have a very good notion regarding the variability of the effect size. So here is the combined base factor. On the right-hand side of the axis, we plot the logarithm of the combined base factor, and these are the logarithm of the individual base factor for each of the replicated studies. And as you can see, when the logarithm of the combined base factor goes up to something close to 800, so that gives us an overwhelming evidence in support of the alternative hypothesis.
When reading the base factor functions, what are we looking for in terms of the takeaway feature? Are we looking for the maximum of the curve, or are we looking for the value at certain effect sizes?
So basically, we want to find the evidence for each of the effect sizes, and we also want to know for which effect size we are gaining the maximum evidence for. So that's why we are expressing the base factor as function of the effect sizes.
So the peak, the argmax is.
Yes. That's how we find R. Yeah. So as I mentioned, we have overwhelming support in favor of the true null, in favor of the true alternative hypothesis here. The logarithm of the combined base factor was as high as 774 for large effect sizes like 0.9 or near 1. And here, interestingly, the map estimate of R was around 12. So in the previous case, when the null was favored, it was just 1. And in this case, it's around 12. So here, the red curve denotes the base factor function corresponding to the map estimate of R. And the green curve denotes the base factor function for putting R equals 1. So except near 0.9, we can see that R equals to 1 gives a pretty good estimate. But when the effect sizes was around 0.1, very close to very close to 1, that is around 0.8 or 0.9, the logarithm of the base factor between the map estimate of R and R equals to 1, they differed by a factor of 0.2 and 0.3. So if you exponentiate it, we get quite a difference. So you cannot obtain the maximum evidence using R equals to 1 in that case. But in case you did not have any notion regarding the variability of R, you could choose R equals 1. But in order to gain the maximum evidence, you have to choose the map estimate of R. So this is how the map estimate of R varies with the effect size. So on the vertical axis, I have plotted the map estimate of R. And on the horizontal axis, these are the effect sizes. So around an effect size of 0.8 or 0.9, the map estimate of R was around 12. Concluding the talk, yeah.
Just I guess a little bit. I'm dumb enough question. When you're doing the argmax of the map, how are you doing that in the scenario, for instance, where you thought it where it's a flat function across? In the previous graph, it basically showed that the R estimates for values of omega, one more further. This one is basically flat at 1, leading up between 0 and 0.6 something. So in terms of optimization, how are you not getting stuck at that flat piece? Like, are you using, are you just evaluating on the grid, or are you doing?
No, so basically this is the continuous function of R. So
it's R max. R star is sort of like the R at the top of that. So how are you getting?
I didn't quite get you.
Just from what you have on the slide right now.
Yes.
How are you finding the value of P?
So we just maximize the posterior density of R under the alternative.
Okay. So maybe,
yeah.
So that's why this is not the function you're optimizing per se. Okay.
No. That's not the
function.
It's just how R varies with effect sizes. The map estimate of R varies with. This is not the function that I have. So I'm basically optimizing the marginal density of the test statistic. This is the marginal density of the test statistic. So this is the density proportional to the posterior density of R, the alternative. So that's what I'm maximizing. So some concluding remarks. As I had mentioned that computing base factors while computing base factors, we might encounter computing high dimensional integral. So by calculating base factors based on test statistics, we easily overcome such computational difficulties. We also reflect effects. We could also reflect effect sizes within base factors. Usually practitioners have an idea about the effect size they are testing for, so we could easily reflect that. And through that, we can also determine the effect size for which or against which we have the maximum evidence for. We could effectively take into account the variability and the dispersion of the effect sizes, and that helps us to extend the idea of base factor for replicated studies. And we also enhance the interpretation of the base factor in a sense, because we could remove the subjectivity of prior specifications, since we specify the prior modes on the standardized effect sizes. And under the null distribution, we do not have to specify any priors. So these are the references. Put it on archive. So there are a few more examples.
Any questions?
So you said it saves computational complexity, especially in contrast to the method you compared to. What exactly are they doing that's difficult to your age?
Yes, so
it seems like a relatively simple setting. It's still a little bit complicated with that.
yes, so in the competing method, you have to find the marginal. So there are 5 parameters involved. So you basically have to compute a high-dimensional integral in order to find the margin. So this is a relatively simple setup, but in the paper we have shown a difficult setup as well, which was a chi-square test. So in that case, there is a high-dimensional integral involved, and the computing the marginal becomes very cumbersome. And also, you are specifying some subjective priors on all the parameters, so there are kind of accumulates. In our case, it's just a unidimensional parameter.
So you had a plot where you show a bunch of scatter plots and you say that they are assuming normally to be a non-issue. But when you were defining your base vector based on 16, are you not making it up?
No, so basically, I'm considering a Fisher Z transformation of the correlation coefficient, but I do not have any assumption regarding the underlying distribution of the data.
So you assume that your sample size is large.
Yes, we had marginal samples. So when you have replicated studies, you also. So usually, if you accumulate the sample size across replications,
Any more?
I have a question. You said that in this slide, it says that y differs the population correlation for the highest study. And in somewhere you also said that you assume rho to be the common.
So I did not index it with I. So rho is the general correlation coefficient, the correlation coefficient you're testing for.
Right.
So you want to test if persistence and conscientiousness are correlated or not. And you collect the data at different sites, say Texas and Arkansas, like that.
Okay,
so rho
like
I yes, exactly. Rho I at the population correlation coefficients at the ith site, but rho is the population correlation coefficient that you're trying to test for.
That's it. Give another round of applause. Thanks for coming.